When we imagine the inside of a neutron star, we are already in unfamiliar territory. The outer layers are strange enough, a rigid crystalline crust unlike anything on Earth, beneath which lies a sea of neutron superfluid threaded with quantized vortices and superconducting protons. But deeper still, as one journeys toward the very heart, the physics becomes not only exotic but uncertain. The pressures rise to such extremes that even neutrons, once thought to be the ultimate building blocks of stellar remnants, may give way to still more fundamental constituents. This is the heart of the diamond, the inner core, where theory, speculation, and mystery collide. At the surface of a neutron star, the density is already greater than anything found in ordinary matter. Descend to the interior, and the numbers quickly become staggering. By the time we reach the core, densities are several times greater than that of an atomic nucleus, on the order of 10-15 grams per cubic centimeter. This means that a single teaspoon of core matter would outweigh a mountain. But what precisely exists under such crushing conditions? That question remains one of the great puzzles of astrophysics. The simplest assumption is that the inner core is made almost entirely of neutrons, packed together so tightly that their individual identities blur. For many years, this neutron matter model dominated. Yet nature rarely remains so simple. At such extreme densities, the forces between neutrons allow for new possibilities. The neutrons might transform into particles known as cousins of the neutron and proton that contain strange quarks in addition to the usual up and down quarks. Hyperons, particles like the lambda, sigma, and xi, are normally unstable in laboratories, decaying almost instantly. But in the suffocating density of a neutron star's core, they may be stabilized, becoming part of the fabric of matter. The introduction of hyperons changes everything. They alter the way matter resists compression, softening the equation of state, the mathematical relationship between pressure and density. This, in turn, changes the maximum mass a neutron star can support before collapsing into a black hole. If hyperons are present, stars may collapse at lower masses than previously expected. Observations of neutron stars that are heavier than 2 solar masses, however, challenge this picture, suggesting that either hyperons are somehow suppressed or that new physics counterbalances their softening effect. This tension between observation and theory is known as the hyperon puzzle, a riddle at the heart of the diamond. Even stranger possibilities lurk deeper still. Neutrons themselves are not fundamental. They are built of quarks, the tiniest particles we know, bound together by the strong nuclear force. Under ordinary conditions, quarks are confined within neutrons and protons, never seen in isolation. But under the enormous pressures of a neutron star's inner core, confinement may break down. Neutrons might dissolve into a soup of free quarks, up, down, and perhaps strange quarks mingling in a new state of matter-quark matter, if it exists, would represent a profound shift. Instead of particles bumping against each other, we would have a continuous sea of fundamental components, moving more freely but still bound by the strong force. Some theorists have gone further, suggesting that quark matter could form paired states analogous to superconductivity or superfluidity. The inner core, then, could be a realm where matter is both fluid and ordered, where the strong force arranges quarks into vast, coherent patterns. If strange quarks are present in abundance, the mixture of up, down, and strange quarks may be more stable than ordinary nuclear matter. If true, then the core of a neutron star might not only contain strange quark matter, it might be entirely made of it, creating what some call a strange star. Stranger still, such matter might be stable even outside the conditions of the star, raising the unsettling possibility that a fragment could persist if somehow ejected. Though speculative, this idea captures the imagination, suggesting that hidden within the universe are droplets of matter more stable than the atoms that make up our world. The challenge, of course, is that we cannot peer directly into a neutron star's core. All of this remains inference and speculation, guided by theory and constrained by observation. The densest matter we can create in laboratories comes from heavy ion collisions in particle accelerators, where gold or lead nuclei are smashed together at near light speeds. These collisions briefly produce temperatures and densities where quarks roam free, creating tiny flashes of quark-gluon plasma. But those experiments probe high temperatures and relatively low pressures, the opposite of the cold, crushing interiors of neutron stars. Bridging the gap between experiment and cosmic reality requires extrapolation. models, and educated guesses. Astronomers turn, then, to the stars themselves for clues. The mass and radius of a neutron star carry the imprint of its internal physics. By observing how neutron stars deform under tidal forces in binary systems, or how they vibrate after starquakes, scientists hope to infer the stiffness of matter inside. Gravitational wave detections, like those from colliding neutron stars observed by LIGO and Virgo, have opened a new window, providing constraints on the equation of state that may one day reveal whether hyperons, quark matter, or stranger states truly exist at the heart of the diamond. There is beauty in this uncertainty. The inner core of a neutron star is one of the few places in the universe where our knowledge of physics reaches its edge and then falters. It is a natural laboratory where gravity, quantum mechanics, and the strong nuclear force all converge at once, creating conditions we cannot reproduce anywhere else. Every speculation about hyperons, quark matter, or strange stars is not just wild fantasy. It is an attempt to sketch the boundaries of the possible, to understand how matter behaves when pushed to its ultimate limit. Perhaps one day, as observations sharpen and theories evolve, the riddle will resolve. We may learn that hyperons populate the core in abundance, or that quark matter forms a seething sea, or that strange matter lurks, rewriting our understanding of stability itself. Until then, the heart of the diamond remains mysterious, a hidden chamber in the cosmos where matter sheds its ordinary form and becomes something utterly new. The journey inward reveals not only the power of collapse, but the creativity of nature, which fashions order, fluidity, and perhaps even new phases of existence out of unimaginable pressure. The inner core of a neutron star is not just dense, it is transformative, a place where matter itself is reinvented. To imagine it is to confront the limits of knowledge and to recognize that even now, the universe keeps secrets deeper than any we have yet uncovered.
When we stand back and look at the neutron star as a whole, the picture that emerges is one of astonishing complexity. From a distance, it appears deceptively simple, a compact sphere, only a few tens of kilometers across, a dot of darkness against the backdrop of space, perhaps flashing beams of radiation, if it is a pulsar. Yet inwardly, this object is layered like an onion, each shell more alien than the last, each transition marking a new frontier in the behavior of matter. To trace these layers is to embark on a journey through a miniature universe where gravity, quantum mechanics, and nuclear forces sculpt landscapes stranger than any planet or star we know. The outermost layer is the crust, the first barrier encountered by anything falling toward the star. Unlike the turbulent gaseous surfaces of ordinary stars, this crust is crystalline, rigid, and extraordinarily strong. The nuclei of atoms arrange themselves into lattices, frozen in place by pressure, while electrons flow freely in a degenerate sea. This is not a thin veneer, but a shell hundreds of meters thick, hard enough to support mountains, though mountains here are only centimeters tall, crushed flat by the star's colossal gravity. This crust is the perfect diamond, a Coulomb crystal spanning the circumference of a world. It is unimaginably stronger than steel, billions of times more resilient than any material on Earth, and it forms the foundation of the neutron star's stability. Beneath this solid lattice, the order begins to shift. The nuclei grow more neutron-rich as pressure increases, until eventually the neat crystalline structure gives way to something new and bizarre. Here we enter the so-called nuclear pasta layer, where matter adopts shapes unlike anything seen on Earth. Instead of spheres, the nuclei stretch into rods, sheets, and labyrinthine structures, sculpted by the tug-of-war between nuclear attraction and Coulomb repulsion. These bizarre geometries, nicknamed spaghetti, lasagna, gnocchi, are not culinary jokes, but serious attempts to describe the lowest energy configurations possible under such conditions. This layer is as much a testament to the creativity of nature as to its strangeness. It marks the boundary where familiar nuclear matter begins to blur, setting the stage for the even stranger depths below. Continuing inward, the rigid structures dissolve, and matter becomes a fluid. This is the great ocean of the star, a neutron superfluid threaded with superconducting protons and permeated by a background of degenerate electrons. The neutrons here flow without resistance, an eternal current that never dissipates energy. They can rotate only in discrete quantum vortices, filaments of circulation that thread the entire fluid, dictating the spin of the star. These vortices pin and unpin against the crust, giving rise to sudden glitches in pulsars, moments when the star abruptly changes its rotation rate. The ocean is not still, it is restless, governed by quantum mechanics on a cosmic scale. In this realm, gravity no longer acts alone. Quantum effects, normally hidden at atomic scales, expand to dominate the motion of kilometers-wide currents. The superfluid behaves with eerie precision, conserving energy and angular momentum across spans of time that dwarf human imagination. Here, the star reveals its dual nature, collapsed to extraordinary density, yet paradoxically alive with motion, an ocean of quantum perfection encased in crystalline armor. Deeper still, at the very core, the certainty of science begins to fade, replaced by speculation and theoretical possibility. The density has now reached several times that of an atomic nucleus. In such conditions, neutrons may no longer remain neutrons. The core might become populated with hyperons, particles like the lambda and sigma, which contain strange quarks. Normally fleeting in laboratories, these exotic cousins may find stability here, changing the pressure balance of the star. Their presence would soften the equation of state, altering the maximum mass a neutron star could support before collapsing into a black hole. Yet the very existence of heavy neutron stars, measured at over 2 solar masses, challenges this possibility, leaving the hyperon puzzle unresolved. If hyperons are not the answer, perhaps quark matter is. Neutrons and protons themselves might dissolve into their fundamental quark constituents, creating a quark-gluon plasma at the heart of the star. In this scenario, the innermost region is not made of individual particles at all, but of a seething soup of up, down, and strange quarks. This quark matter might even adopt exotic states of order, such as color superconductivity, where quarks pair in patterns that minimize energy in ways beyond our current comprehension. Some theorists suggest that strange matter, quark matter with a high proportion of strange quarks, could be more stable than any known form of matter. If so, then neutron stars might secretly be strange stars, their entire cores transformed into something fundamentally new. The layered structure of the neutron star thus resembles a nested universe, each shell governed by its own set of laws. The crust is a crystalline lattice, familiar yet magnified. The pasta layer is a surreal landscape of nuclear geometry. The superfluid ocean is a quantum sea, flowing without friction and whispering in glitches and rotations. The core is a place of uncertainty, a laboratory of hyperons, quark matter, or stranger forms still awaiting discovery. Each layer represents not just increasing density, but a step deeper into the unknown, a reminder that nature's creativity is inexhaustible. To speak of a universe in a sphere is no exaggeration. In a volume scarcely the size of a city, the neutron star encapsulates phenomena that touch on every corner of physics: crystallization, quantum fluids, superconductivity, nuclear matter, and the possible dissolution of particles into their quark foundations. It is a microcosm of the cosmos, compressing into one body the lessons of matter, energy, and fundamental forces, and yet, for all our theories, the neutron star keeps its secrets. We cannot drill into it. We cannot reproduce its pressures in any laboratory. Our only glimpses come indirectly, through the timing of pulsars, the flicker of X-rays, the ripples of gravitational waves. From these distant signals, we reconstruct the hidden layers, like archaeologists inferring civilizations from fragments of pottery. Each new observation narrows the possibilities, but the heart of the star remains shrouded in mystery. Perhaps that is what makes the layered structure so compelling. It is not merely a scientific curiosity, it is a metaphor for our own search for a knowledge. We peel away one layer, only to find another beneath, stranger and more difficult to grasp. The crust leads us to the pasta to the quantum sea, the sea to the speculative core. Each step inward deepens the mystery until we arrive at the edge of our theories, forced to admit that we do not yet know what lies within. A neutron star, then, is more than a stellar remnant. It is a map of physics under extremes, a condensed cosmos, a universe in a sphere. To understand it is to stretch our imagination as far as it will go, to follow matter from its familiar forms into its most alien incarnations, and to recognize that even in a world the size of a city, the universe hides infinities. When a massive star dies, its outer layers are blasted into space in a titanic supernova, leaving behind a collapsed remnant only a few tens of kilometers across. Yet this remnant, the neutron star, is not simply dense, it is also fast. Conservation of angular momentum ensures that as the star shrinks, its rotation rate increases, just as a figure skater spins faster by pulling in her arms. The result is one of the most extreme mechanical phenomena in the universe: newborn neutron stars spinning hundreds of times per second, so rapidly that they exist at the very edge of physical possibility. To understand this, consider the progenitor star. A massive star before collapse rotates relatively slowly, completing one turn in days or even weeks. Its radius might be millions of kilometers. When its core collapses in the supernova, that radius shrinks from thousands of kilometers to barely 20. Angular momentum, however, is conserved. What was once spread across a star the size of Jupiter is now crammed into a sphere the size of a city. The mathematics is relentless. The rotation rate must skyrocket. Newborn neutron stars can therefore spin with periods as short as 1 or 2 milliseconds. Imagine an object larger than Manhattan turning on its axis more than 500 times every second. The surface speeds at the equator can reach tens of thousands of kilometers per second, a few percent of the speed of light. At these velocities, the distinction between mechanics and relativity blurs. Time dilation and frame dragging effects, subtleties of Einstein's general relativity, become relevant in describing what is, at its heart, an astronomical gyroscope. Such extreme rotation is not merely a curiosity. It has profound effects on the structure and behavior of the neutron star. For one, the star is no longer perfectly spherical. The centrifugal force caused by rapid spin deforms it into an oblate spheroid, bulging at the equator. The faster the rotation, the greater the deformation. There exists a theoretical limit, the breakup frequency, beyond which the centrifugal force at the equator would overcome gravity, flinging matter into space. Calculations suggest that neutron stars cannot spin much faster than about 1.5 milliseconds per rotation. Nature, intriguingly, seems to obey this boundary. No neutron star has ever been observed spinning faster. But even below this ultimate limit, the spin is strong enough to shape the star's fate. The rapid rotation influences the magnetic field, amplifying and twisting it during formation. Newborn neutron stars often emerge as magnetars, with fields trillions of times stronger than Earth's, their rotational energy feeding intense electromagnetic outbursts. The spin also dictates the beam of radiation emitted from pulsars, the cosmic lighthouses that sweep their signals across the galaxy with astonishing regularity. The precise ticking of these beams, some flashing hundreds of times per second, is one of the most accurate clocks in nature. The rotational energy of a newborn neutron star is immense. A millisecond pulsar stores more rotational energy than the Sun emits in years. Yet this energy is not eternal. The star gradually slows, shedding energy through magnetic braking, radiation, and interactions with its surroundings. In the first seconds and minutes after birth, the star may lose much of its spin, converting its rotational energy into bursts of high-energy radiation and shock waves that help drive the supernova remnant outward. The afterglow of the supernova in some cases may owe much of its brilliance to this initial spin-down phase. Rotation also introduces instabilities. A rapidly spinning neutron star is not necessarily stable. It may quiver, vibrate, or wobble. Such oscillations can generate gravitational waves, ripples in spacetime that carry angular momentum away from the star. These waves are faint but detectable in principle, and efforts are underway with detectors like LIGO and Virgo to search for them. A newborn neutron star might therefore announce its birth not only through light, but through gravitational whispers, carrying information about its spin and structure directly to our instruments. As the star ages, its spin slows, but the legacy of its initial velocity endures. Some neutron stars are later recycled in binary systems, spun back up as matter from a companion star accretes onto them. These recycled pulsars can once again reach millisecond periods, shining with beams of radio waves so stable that they rival atomic clocks. But the seeds of this behavior lie in the newborn phase, when the collapse first drives the spin to the edge of reality. There is also the fascinating possibility that rapid rotation temporarily prevents collapse into a black hole. If the progenitor star is massive enough, its core might, under static conditions, exceed the maximum mass a neutron star can support. Yet the centrifugal force of rapid spin can provide extra support, delaying collapse. In such cases, a hypermassive neutron star may exist only briefly, rotating violently until angular momentum is lost, at which point the star finally succumbs and becomes a black hole. These fleeting objects are thought to play a role in short gamma-ray bursts, some of the most energetic explosions in the universe. The human imagination struggles to grasp such numbers. A city-sized object spinning hundreds of times per second defies intuition. On Earth, the fastest man-made machines rotate thousands of times per minute, not per second, and at scales only millimeters wide. A neutron star outpaces these by orders of magnitude, all while weighing more than the Sun. Its crust, ocean, and core endure stresses beyond comprehension, yet they do not tear apart. Instead, they balance on the knife edge of physics. Rotation and gravity locked in a precarious dance. Ultimately, the incredible rotational speeds of newborn neutron stars remind us of the uncompromising power of conservation laws. Angular momentum is not optional, it must be preserved. When the universe compresses the vastness of a star into a sphere the size of a city, the spin has nowhere to go but faster. The result is a cosmic whirl, a beacon of both radiation and mystery, pushing matter to its mechanical limits and giving astronomers one of their most precise and fascinating tools for probing extreme physics. At the edge of reality, where gravity, quantum mechanics, and relativity converge, neutron stars spin. Their pulses cross galaxies, their instabilities whisper in gravitational waves, their deformation hints at new forms of matter within. Each newborn neutron star is a testament to the raw arithmetic of the cosmos: compress, conserve, accelerate. In that furious first spin lies not only the story of collapse, but also the seeds of the universe's most extraordinary phenomena. When astronomers first detected the regular pulses of radio waves in 1967, they were baffled. The signals were so precise that at first they were nicknamed LGM, Little Green Men, because no natural source seemed capable of such clockwork regularity. It did not take long, however, to realize that the pulses were not artificial, but astrophysical, originating from neutron stars spinning in the depths of space. These objects, now called pulsars, are among the most remarkable beacons in the universe. Their very existence owed to what has come to be known as the lighthouse effect. To understand this phenomenon, one must begin with the neutron star itself. As the collapsed core of a massive star, it is extraordinarily dense, but it is also endowed with immense magnetic fields. When the progenitor star collapsed, its magnetic field lines were squeezed inward, just as its mass was, amplifying the field strength. What was once a modest stellar magnet becomes something millions to trillions of times stronger than Earth's magnetic field. In some neutron stars, especially magnetars, this magnetic intensity is so vast it can distort atomic orbitals and change the properties of matter itself. The magnetic field is not neatly aligned with the star's spin. Instead, in most cases, the magnetic poles are tilted relative to the rotation axis. This misalignment is the key to the lighthouse effect. Along the magnetic poles, charged particles are accelerated to near the speed of light, following the field lines outward. In the process, they emit beams of electromagnetic radiation, radio waves, X-rays, or even gamma rays, depending on the star's properties. These beams are narrow, collimated, and incredibly intense, streaming into space in opposite directions. Now imagine the neutron star rotating. With each spin, the beams sweep through space like the light from a lighthouse on a dark shore. If Earth lies in the path of one of these beams, we see a pulse of radiation each time it passes over us. The pulses are not produced by the star blinking on and off. They are continuous beams sweeping through space. But to a distant observer, the effect is identical to a light that flashes with every rotation. This is the essence of the pulsar, a cosmic lighthouse whose timing can be astonishingly precise. The regularity of pulsar signals rivals and in some cases exceeds that of atomic clocks. Some millisecond pulsars, spun up by accretion from companion stars, rotate hundreds of times per second with deviations in timing of only a few millionths of a second over years of observation. Such stability has turned pulsars into natural laboratories, used to test general relativity, probe the interstellar medium, and even search for gravitational waves through networks of precisely monitored signals. Yet the lighthouse effect is not just a matter of geometry and timing, it is also a story of energy. The rotational energy of the neutron star powers the beams. Each sweep carries away a fraction of the star's spin, gradually slowing it down over time. A young pulsar, born from a recent supernova, may spin several times per second. Over millions of years, as it radiates away energy, its spin slows, the beams weaken, and eventually the pulsar falls silent. This evolutionary path explains why pulsars are most often found in supernova remnants or in binary systems. Where fresh angular momentum can be added, the lighthouse effect also reveals itself in the richness of pulsar behavior. Some pulsars exhibit glitches, sudden increases in rotational speed caused by the unpinning of vortices in their neutron superfluid interiors. Others drift in pulse shape or intensity, showing that the magnetosphere, the zone of charged particles surrounding the star, is dynamic and complex. These variations add texture to the otherwise clock-like signals, giving astrophysicists clues about the physics of matter and magnetism under extreme conditions. The pulsar's beam itself is not uniform. Observations suggest that it often has a conical shape, with different regions emitting different kinds of radiation. Radio waves, for example, may originate closer to the star's surface, while high-energy X-rays and gamma rays emerge from higher up in the magnetosphere. Depending on where Earth cuts through this cone, we may see strong signals, weak ones, or none at all. This geometry explains why only a fraction of neutron stars appear to us as pulsars. Their beams simply do not sweep across our line of sight. Many silent neutron stars must exist, hidden from view despite their furious rotation. The lighthouse effect also connects neutron stars to some of the most energetic events in the cosmos. In certain cases, the energy released by the beams is so great that it drives observable nebulae. The Crab Nebula, for example, is lit by its central pulsar, whose beams inject energy into the surrounding gas, creating a glowing cloud that has been expanding since the supernova of 1054 CE. Here, the lighthouse is not just a signal, but a cosmic engine, shaping the environment on a scale far larger than the star itself. In binary systems, the effect takes on another layer of complexity. A pulsar locked in orbit with a companion star can accrete matter, twisting its magnetic field and altering its beams. Sometimes the beams themselves interact with the companion, heating its surface or even stripping material from it. In such systems, the lighthouse is not an isolated beacon but part of a dynamic dance, its light and magnetism altering everything in its reach. The discovery of pulsars transformed astrophysics because it revealed not just a new type of star, but a mechanism, a rotating lighthouse of radiation that could be understood in precise detail. The elegance of the lighthouse effect lies in its simplicity, misaligned magnetism, rotation, and beams. Yet the consequences are vast: cosmic clocks, engines of nebulae, laboratories for fundamental physics. When Jocelyn Bell Burnell first noticed those regular pulses on her radio telescope charts, she had no way of knowing she was glimpsing the sweep of beams from a collapsed star spinning on the edge of physical possibility. Today, we know that each pulse is the blink of a lighthouse across unimaginable distances, a beacon that ties together gravity, magnetism, quantum mechanics, and relativity in a single flash of light. The lighthouse effect is, at its heart, a cosmic story of visibility. Neutron stars are everywhere, but only some shine as pulsars, their beams crossing our planet's line of sight. For every beacon we see, many more sweep invisibly in the dark. The universe is filled with these rotating lighthouses, each pulse a reminder that even in the silence of space, nature finds a way to make itself known.
Among the countless wonders of the universe, few rivaled the astonishing regularity of pulse. These rotating neutron stars, born in the violent aftermath of supernova, are already extraordinarily dense beyond comprehension, magnetized beyond imagination, and spinning at dizzying speeds. Yet what elevates them to a realm of their own is their timing. Pulsars tick with such precision that they rival, and in some cases surpass, the best atomic clocks on Earth. They are the universe's timekeepers. Cosmic clocks, whose beats can measure not only the passage of seconds but the very fabric of spacetime itself. To appreciate the scale of this precision, consider a millisecond pulsar. These are neutron stars that spin hundreds of times per second, sending beams of radio waves sweeping past Earth with each rotation. For certain pulsars, the timing of these pulses is so consistent that their deviations amount to less than a millionth of a second over years of observation. Imagine a clock that ticks perfectly for decades, barely straying from its rhythm despite being battered by magnetic storms, gravitational tides, and the lingering chaos of its supernova birth. That is the marvel of the cosmic clock. Why are pulsars so precise? The answer lies in their nature. A neutron star is a rigid body of immense density. Its crust is harder than diamond, its interior a superfluid that resists dissipation, and its rotation locked by angular momentum, so enormous that external torques have almost no effect. Once set spinning, the star becomes a gyroscope of cosmic scale. The beams we detect are a direct consequence of this spin, tied to the magnetic poles sweeping through space. Every pulse is a rotation, and every rotation is an act of near-perfect consistency. Millisecond pulsars in particular achieve extraordinary stability thanks to their history. Unlike young pulsars, which spin down quickly as they radiate energy, millisecond pulsars have been recycled. In binary systems, matter from a companion star accretes on to the neutron star, transferring angular momentum and spinning it up to blistering speeds. This process also smooths out irregularities, creating a star whose rotation is extraordinarily steady. The result is a cosmic metronome, a star the size of a city keeping time with the reliability of engineered perfection. The practical consequences of this precision are profound. Astronomers use pulsar timing to measure distances, test theories, and probe the unseen. For example, the orbital decay of the famous Pulse-Stellar binary pulsar 2 neutron stars locked in a tight dance was measured so precisely that it revealed the emission of gravitational waves decades before direct detection was possible. The loss of orbital energy matched Einstein's predictions to within a fraction of a percent, offering one of the most stunning confirmations of general relativity ever achieved. Pulsar timing has also allowed scientists to weigh neutron stars with exquisite accuracy. By monitoring the arrival times of pulses as a neutron star orbits a companion, astronomers can calculate the mass of both objects and constrain the dense matter equation of state. In some cases, these measurements have revealed neutron stars more massive than 2 suns, forcing theorists to reconsider what forms of matter can exist in their cores. The cosmic clocks, in effect, tell us not only the time but also the limits of matter itself. But perhaps the most ambitious use of pulsar timing lies in the search for gravitational waves at the largest scales. By monitoring an array of millisecond pulsars spread across the sky of pulsar timing, array scientists hope to detect the faint ripples in spacetime caused by supermassive black holes orbiting each other in distant galaxies. As a gravitational wave passes between Earth and a pulsar, it subtly alters the distance the pulses travel, shifting their arrival times by tiny fractions of a second. Detecting these changes requires timing, stability over decades, and pulsars provide just that. In 2023, international collaborations announced compelling evidence that pulsar timing arrays are indeed sensitive to a background hum of gravitational waves pervading the universe. The beauty of pulsar timing is that it translates astrophysical violence into precision measurement. These stars, born in the collapse of titans, spinning at relativistic speeds, and threaded with magnetic fields strong enough to crush atoms, somehow give rise to the most delicate and exact tools of observation. Every pulse that reaches us is not just a flash of radio energy, it is a tick of a natural clock, a measure of rotation so consistent that it can chart the curvature of spacetime itself. There is also something deeply poetic in this. On Earth, we laboriously engineer atomic clocks, using the vibrations of cesium atoms to define the second. In the cosmos, without our intervention, nature has created its own clocks, ticking with fidelity that challenges our finest machines. These clocks are scattered across the galaxy, each one a reminder that the universe has its own metronomes, set into motion long before humanity learned to measure time. Yet pulsar clocks are not perfect. They drift, slow, or occasionally glitch. A glitch occurs when the star's superfluid interior transfers angular momentum suddenly to the crust, speeding up its spin by a tiny but measurable amount. These events disrupt the clock-like precision, but they also provide clues about the star's interior, offering rare glimpses into physics under pressures we cannot reproduce. In this way, even the imperfections of pulsar clocks become scientific treasures, encoding information about the hidden quantum sea beneath the crust. The cosmic clocks also extend our vision across space and time. By comparing the pulses of many stars, astronomers can construct a galactic-scale observatory, with each pulsar acting as a distant, synchronized beacon. Together, they form a network that can detect disturbances too vast for any human-built detector. From colliding black holes millions of light-years away to subtle changes in the Earth's own orbit, the galaxy itself becomes a laboratory, and pulsars are its ticking instruments. In the end, pulsars remind us that time is both a human invention and a cosmic reality. We define seconds, minutes, and hours to order our lives, but in the universe, time is kept by the rotation of collapsed stars. Their pulses are ancient rhythms, carrying across light-years to reach our telescopes. Each one is both a beat of a clock and a message from the extreme frontier of physics. To call them cosmic clocks is no exaggeration. They are clocks not only in precision but in significance, turning the collapse of massive stars into tools of measurement that stretch from the atomic scale to the galactic. In every tick lies a piece of the universe's story: how stars die, how matter behaves under crushing densities, how gravity bends spacetime, and how the universe itself hums with waves we are only beginning to hear. When humans first crossed oceans, they looked to the stars for guidance. Sailors memorized constellations, charted the positions of the sun and moon, and used sextants to fix their course. Today, spacecraft crossing the solar system rely on radio signals from Earth, triangulated by giant antennas, to know where they are. But as we dream of venturing farther to the outer planets, or one day to interstellar space, we confront a sobering reality. Earth-based navigation will not suffice. Signals take hours to reach the farthest probes, and beyond that, delays stretch into days and weeks. What is needed is a celestial navigation system, one not tied to Earth, but written into the cosmos itself. Remarkably, nature has already provided such a system. Pulsars. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across the sky like the searchlight of a lighthouse. To an observer aligned with the beam, the star appears to flash at regular intervals, sometimes hundreds of times per second. These flashes are not random, they are extraordinarily precise. In fact, millisecond pulsars keep time as reliably as the best atomic clocks. Their regularity, combined with their distribution across the galaxy, makes them ideal candidates for navigation. Each pulsar is, in effect, a cosmic beacon, broadcasting a unique timing signature into space. The principle of pulsar navigation is straightforward in concept. Just as GPS satellites on Earth send timing signals that allow receivers to calculate their position, pulsars can do the same for spacecraft. A vessel equipped with an X-ray or radio detector can measure the arrival times of pulses from several known pulsars. By comparing these times to predictions based on pulsar timing models, the spacecraft can triangulate its position in space with remarkable accuracy. Unlike Earth-based communication, this method is autonomous. The spacecraft does not need to ask Earth where it is. The universe itself provides the map. The advantage of pulsars lies in their constancy. They are scattered across the galaxy, many visible from anywhere in space, and their signals are not subject to interference or drift like artificial transmitters. Each pulsar has a unique fingerprint, its period, pulse shape, and timing history that distinguishes it from all others. A catalog of pulsars thus becomes a galactic reference frame, a celestial grid that can anchor navigation far beyond the reach of terrestrial methods. NASA has already demonstrated this principle. In 2017, the Sexton experiment, Station Explorer for timing and navigation technology aboard the International Space Station, successfully used X-ray observations of pulsars to autonomously determine the station's position in orbit. By observing for millisecond pulsars and comparing their pulse arrival times to models, the system pinpointed the ISS's location to within a few kilometers. Though modest compared to GPS accuracy on Earth, the result was revolutionary, a proof of concept that spacecraft could navigate independently using natural beacons. With refinement, pulsar navigation could guide spacecraft across the solar system with accuracies of tens to hundreds of meters, and across interstellar distances with comparable precision to what GPS provides us on Earth. This idea is not merely theoretical, it has already been woven into the story of human exploration. The plaques carried aboard the Pioneer 10 and 11 probes, launched in the 1970s, include a map showing the positions of 14 pulsars relative to the Sun. Each pulsar is identified by its period, etched in binary, allowing any civilization that finds the plaque to locate our solar system in space and time. It is perhaps the most literal map to the stars ever created, one that relies on the universality of pulsar timing to say, here we are. Now. The uses of pulsar navigation extend beyond simple positioning. Because pulsars are distributed across the galaxy, they provide not only location but orientation. A spacecraft could determine its attitude, how it is rotated in space, by comparing the apparent timing of multiple pulsars. This capability would be invaluable for deep space missions, where gyroscopes drift and star trackers may be obscured. Pulsars, indifferent to spacecraft conditions, remain fixed beacons. Anchoring a vessel in the cosmos, there are challenges, of course. Pulsars are faint, and their signals must be carefully extracted from background noise. X-ray pulsars, in particular, require sensitive detectors, though advances in compact X-ray optics and electronics have made such instruments feasible for spacecraft. Timing, noise, and glitches in pulsars can also introduce uncertainty, but these are well studied and can be accounted for with models. With continued refinement, a practical pulsar navigation system could become as indispensable to interstellar travel as GPS is to daily life on Earth. The philosophical implications are as striking as the technical ones. For millennia, humans have looked to the heavens for direction. The North Star guided ancient travelers, while sextants aligned with the sun and moon kept ships on course. Now, as we prepare to voyage into interstellar space, we return once more to the stars, not figuratively but literally. Pulsars, the remnants of dead suns, will guide us across the void, their ticking beams marking our place in the galaxy. The irony is beautiful. The death of massive stars has given birth to the tools of cosmic navigation. This perspective also underscores the universality of pulsars. Any advanced civilization could, in principle, use them for navigation. The pulsar grid is not ours alone, it is a galactic map available to any who can detect and interpret the signals. The Pioneer plaque anticipated this truth, encoding a message in pulsar periods that any astronomers, anywhere, might understand. In this sense, pulsar navigation is not only practical but also communicative, a shared language written in the pulses of collapsed stars. Looking ahead, pulsar navigation may become the backbone of interstellar travel. As spacecraft venture farther from Earth into regions where radio signals take years to traverse, autonomy will be essential. Missions to the outer solar system could use pulsars to stay on course without waiting for Earth-based corrections. Interstellar probes like those imagined by Breakthrough Starshot or future human expeditions could use pulsars to maintain orientation across light. The map is already drawn, we need only to learn how to read it with precision. In the end, pulsar navigation represents a profound convergence of science and exploration. What began as an astrophysical curiosity, flashing radio signals, mistaken for little green men, has become a cornerstone of humanity's future in space. The lighthouse beams of neutron stars, sweeping tirelessly across the galaxy, are not just reminders of stellar death. They are also promises that even in the vast darkness there are beacons to guide us, maps to follow, and clocks to trust. With pulsars, the stars themselves become our compass, and the galaxy our sea.
Among the many varieties of neutron stars, one class stands apart as both awe-inspiring and terrifying: magnetars. If a normal neutron star is already extreme, a magnetar is its monstrous sibling, rarer, more volatile, and endowed with the most powerful magnetic fields known in the universe. These stars are the ultimate expressions of stellar collapse, where density, gravity, and magnetism conspire to create a phenomenon so exotic that it defies ordinary comparison. To understand magnetars, we must first recall the already staggering nature of a typical neutron star. Take the mass of the Sun, compress it into a sphere no wider than a major city, and you have an object whose density rivals atomic nuclei. The surface gravity is immense, the crust is harder than diamond, and the interior may harbor strange forms of matter beyond human comprehension. Yet even among these titans, magnetars distinguish themselves. Their defining feature is a magnetic field of almost inconceivable strength, on the order of 10^14 to 10^15 Gauss. By contrast, Earth's magnetic field measures less than 1 Gauss, and the strongest laboratory magnets humans have ever constructed barely reach 10^5 Gauss. A magnetar's field is trillions of times stronger than anything we can create, a field so powerful it warps the very vacuum of space. What does such a magnetic field mean in practice? For one, it reshapes the star's environment. In the vicinity of a magnetar, atoms cannot exist in their usual form. The overwhelming magnetic force elongates atoms into needle-like shapes, crushing their electron clouds and binding them far more tightly than normal. Chemistry as we know it ceases to exist. Even photons, the fundamental particles of light, are affected. Quantum electrodynamics predicts that under such conditions, the vacuum itself becomes birefringent, meaning light behaves differently depending on its polarization. In other words, a magnetar bends the rules of optics, forcing empty space to act like a crystal. The origins of such fields are still debated, but most models suggest that magnetars form when a massive star's core collapses, and conservation of magnetic flux amplifies the pre-existing magnetic field to monstrous levels. If the newborn neutron star also spins rapidly, a dynamo effect may drive the field even higher. Whatever the precise mechanism, the result is an unstable, short-lived phase of stellar evolution. Magnetars are thought to be relatively young, less than 10,000 years old, because their magnetic fields decay quickly on astronomical timescales. As the fields weaken, the star settles into a more ordinary neutron star. But during their youth, they are cosmic engines of violence. This violence manifests most dramatically as magnetar outbursts. Occasionally, stress in the star's crust, caused by the shifting and twisting of magnetic fields, reaches a breaking point. The crust cracks, releasing a sudden burst of energy. These starquakes unleash enormous flares of X-rays and gamma rays, sometimes visible across the galaxy. The most powerful of these events, known as giant flares, can momentarily outshine all other X-ray sources in the sky combined. One such flare, detected in 2004 from a magnetar about 50,000 light-years away, was so intense that it measurably affected Earth's ionosphere, despite the vast gulf of space. Had the same event occurred within 10 light-years, it could have stripped Earth's atmosphere. The energy scales involved are difficult to fathom. In a fraction of a second, a giant flare from a magnetar can release as much energy as the Sun emits in hundreds of thousands of years. And this violence is not rare in the cosmic sense. We now suspect that some mysterious fast radio bursts, FRBs, millisecond-long blasts of radio energy detected from far beyond our galaxy, may be tied to magnetar activity. If confirmed, magnetars would not only be local monsters, but also producers of signals visible across the observable universe. Living near a magnetar would be impossible. The sheer magnetic field would wreak havoc on matter. At distances of thousands of kilometers, it could disrupt molecular bonds, effectively tearing apart the chemistry of life. Closer still, its field would induce lethal currents in biological tissue, rendering survival inconceivable. Even spacecraft or electronics would be disabled long before reaching the star. Theoretically, if you stood within 1,000 kilometers of a magnetar, the difference in magnetic force between your head and feet would be strong enough to tear you apart at the atomic level. These are not stars to approach. They are stars to observe from the deepest safety of distance. Yet for all their menace, magnetars are also laboratories for fundamental physics. Their conditions push matter and fields to extremes unreachable on Earth. They allow us to test theories of quantum electrodynamics, nuclear physics, and the behavior of matter under crushing densities. Observing their emissions, measuring their flares, and modeling their magnetic evolution all deepen our understanding of how the universe operates at its limits. Magnetars, in this sense, are not just monsters, but teachers. They are also rare. Out of the thousands of neutron stars estimated to exist in our galaxy, only a few dozen magnetars have been confirmed. Their rarity makes each detection precious, a chance to study the most extreme magnetic engines nature has produced. And while they may represent only a brief stage in the life of a neutron star, their influence may extend far. Their flares and bursts inject energy into surrounding space, shaping interstellar environments and perhaps even contributing to the seeding of heavy elements. It is tempting to think of magnetars as cosmic villains, rampaging through the galaxy with destructive power. But, in truth, they are part of the grand tapestry of stellar evolution. They remind us that the death of massive stars is not a quiet process, but one filled with fire, violence, and strange new physics. They are the last gasps of giants, transformed into monstrous beacons whose fury tells us of the extremes possible in nature. If neutron stars are the diamonds of the cosmos, dense, enduring, and brilliant, then magnetars are the diamonds of flame, blazing with the heat of impossible fields. They embody the paradox of astrophysics. From destruction comes knowledge, from collapse comes light, and from death comes a new kind of wonder. To look upon a magnetar is to see the universe at its most unrestrained, a glimpse of what happens when nature pushes itself past the limits of imagination.
Magnetars, with their unfathomable magnetic fields, are not quiet objects. They are restless, volatile, and prone to sudden eruptions of energy that dwarf almost anything else in the universe. Among the most dramatic of these events are starquakes and flares, phenomena that shake not only the magnetar itself, but sometimes even distant planets like our own. To study them is to glimpse the extraordinary stresses that act within these stellar monsters, and to appreciate how fragile even a neutron star's crust can be when confronted with magnetic fields 1,000,000,000,000 times stronger than Earth's. The idea of a starquake might sound poetic, but it is brutally literal. Just as Earth's crust can shift under strain and release energy in an earthquake, the crust of a magnetar, an ultra-dense shell harder than diamond, is constantly under immense stress from the twisting, evolving magnetic fields beneath it. These fields, rooted deep in the neutron star's superfluid interior, can tangle, shear, and reorganize, exerting enormous pressure on the outer layers. Eventually, the crust can no longer withstand the stress. It cracks. When this happens, the released energy is staggering. A starquake can unleash more energy in a fraction of a second than all the earthquakes in human history combined. The fracture sends seismic waves rippling through the neutron star, exciting oscillations in its crust and magnetic field. Unlike an earthquake, however, the effects are not confined to the star itself. Because the magnetic field lines are anchored in the crust, a sudden shift reverberates outward, twisting the magnetosphere, the region of space dominated by the star's field, and triggering explosive releases of electromagnetic radiation. This brings us to magnetar flares. They are the visible signatures of the violence beneath the surface, akin to a cosmic lightning strike following a quake. Flares come in different flavors, from short, sharp bursts of X-rays lasting less than a second to titanic giant flares that can be seen across the galaxy. The smaller bursts are frequent, peppering magnetar observations with rapid flashes that hint at the restless interior. But it is the giant flares that truly capture the imagination. A giant flare begins with an initial spike of gamma rays, an immense blast that rises in less than a tenth of a second. This spike alone can outshine every other X-ray and gamma-ray source in the sky combined. What follows is often a pulsating tail of emission, modulated by the magnetar's rotation, as the magnetosphere rearranges and releases its pent-up energy. The entire event may last only minutes, but the energy output is astronomical, on the order of 1044 ergs or more, equivalent to the Sun's total output over hundreds of thousands of years. The most famous example occurred on December 27, 2004, when the magnetar SGR 1806-20 produced a flare so bright it overwhelmed detectors on multiple satellites. Located about 50,000 light-years away, this single event briefly altered Earth's ionosphere, a feat no other astrophysical object outside the solar system has been known to achieve. Had such a flare occurred within 10 light-years, it might have devastated Earth's atmosphere, stripping away protective layers and exposing the surface to deadly radiation. Thankfully, magnetars are rare, and dangerous proximity is unlikely. But the violence of starquakes and flares is not just destructive, it is informative. These events allow astronomers to probe the interior structure of neutron stars. When a quake occurs, the resulting oscillations in the star's crust and core can leave imprints in the emitted radiation. These quasi-periodic oscillations, or QPOs, have been detected in the tails of giant flares, offering tantalizing clues about the star's composition and the strength of its internal magnetic fields. In essence, each flare is a seismic experiment on a star we cannot touch, a window into matter compressed beyond atomic limits. Moreover, magnetar flares may explain some of the most mysterious cosmic signals. Fast radio bursts, FRBs. These millisecond-long blasts of radio energy, some from billions of light-years away, have puzzled astronomers since their discovery. In recent years, a direct connection was observed when a magnetar in our galaxy produced both an X-ray flare and a simultaneous FRB. If magnetars are indeed the engines behind at least some FRBs, then their starquakes and flares are not only local fireworks but galactic lighthouses, sending signals across the universe. The physics driving these eruptions is a marriage of magnetism, gravity, and quantum mechanics. The magnetic fields, twisted by the star's rotation and internal currents, store colossal amounts of energy. The crust, though unimaginably strong, is brittle compared to the relentless pressure from below. When it gives way, the released energy couples with the magnetosphere, accelerating particles to near-light speeds and producing bursts of radiation. In some scenarios, magnetic reconnection, similar to the process that drives solar flares on our Sun, may also play a role, though on scales vastly beyond anything in our solar system. There is a strange duality in these events. On one hand, they remind us of the fragility of order in extreme environments. Even a neutron star, the endpoint of stellar collapse, can fracture and burst under internal tension. On the other hand, they highlight the resilience of the cosmos. The magnetar does not disintegrate after a flare. It survives, scarred but intact, to flare again. This cycle of stress and release may continue for thousands of years until the magnetic fields decay and the star settles into quiet. For humanity, starquakes and flares are more than curiosities. They are natural laboratories for the study of high-energy physics. Observing them teaches us about the limits of matter, the interplay of magnetic fields and crustal dynamics, and the behavior of plasma under extreme conditions. They also remind us of our place in the cosmos. Here on Earth, we worry about earthquakes and solar flares, but across the galaxy, neutron stars quake and release energies that could sterilize planets. It is a humbling contrast. In the end, the violence of starquakes and flares is part of the magnetar's story. These stars, monstrous though they are also communicators, sending bursts of energy that carry information across the void. They are both destroyers and teachers, warnings and guides. To study them is to confront the universe at its most furious, and to learn that even in its rage, the cosmos reveals its secrets.